Hello, Royals. For lesson 5.4, compound trig identities, I want to show you a couple of options that we have. Let's consider the statement that the cosecant of pi by 2 minus theta is equal to the secant of theta. Without context, it might not be clear what's expected of us. One direction that we might see is asking us to prove this statement to be true. And then I'll give you another direction that often students wouldn't choose to follow that pathway. But given the lessons that we've learned recently, usually students are prone to treat this as an identity. So they do a left side, right side approach, and that's fine. Let's take a look at what that looks like. The left-hand side would be the cosecant of pi by 2 minus theta, which I'm going to treat as the reciprocal of the sine of pi by 2 minus theta. And then I'm going to run a sine difference formula on this. That's going to be the reciprocal of, let's see, a sine of pi by 2 times the cosine of theta minus a cosine of pi by 2 times the sine of theta. And one of our pieces of advice in the lesson was to evaluate when possible. So let's go down here and say, well, the sine of pi by 2 is just 1. So we've got 1 times the cosine of theta minus the cosine of pi by 2 is 0. We should show that to our reader. And then let our reader catch up, because we're not trying to get the answer as fast as possible. We're trying to present a solution that our reader can follow. We get the reciprocal of the cosine of theta, which is going to be the secant of theta, which is the right-hand side. That worked fine, I suppose. Maybe I didn't notice that I just proved the cofunction identity by using the sine sum formula or sine difference formula or cosecant difference formula, I suppose. This is what we need to be ready for. We need to be ready for questions that give us identities that we may be able to prove with the left side, right side approach, but we may be asked to use sketches in standard position to show that it's true. Usually this type of question, I won't tell you what the right-hand side is, and that kind of separates it from what we would call a traditional identity. But let's try using sketches in standard position to illustrate, I guess, the truth of the statement above. So this is a bit of 5.0 again. I'm going to sketch an angle theta. I'm going to go ahead and say that it goes through the point A comma B with a radius of C, and there's theta. Now I'm going to figure out where pi by 2 minus theta would be. If that's theta right there, that would be pi by 2 minus theta. These triangles are going to be similar, and they're going to be congruent. Therefore, the dimensions are the same, but they are inverted, reflected across the line y equals x. So the coordinates there would be b comma a. If I start on the left-hand side, then I suppose I could say that the left-hand side is the cosecant of pi by 2 minus theta, which is going to be pi by 2 minus theta's r value to its y value, which I recognize as the ratio of the r value to the x value for theta. And the ratio of the r value to the x value for theta is the secant of theta. And that actually seemed to go a little bit faster, but it's up to me to sort of spot the diagram. Okay. We can look at other related ratios that we investigated in 5.0 and see how our angle sum formulas would tell us the same answer, I suppose. So we can check for truth there. Let's look at the cosine of pi by 2 plus theta. So say I'm asked to find an expression on theta equivalent to, and I'm given no other directions. I won't be answering questions saying, oh, should I draw this in standard position? If I want you to draw it in standard position, I will tell you to draw it in standard position. I won't answer, oh, should I use the cosine sum formula? These are things you need to decide. And unlike solving equations, I don't think there's a huge disadvantage to using one approach or the other. Let's start with sketches in standard position. Here's theta. I say so, right? Let's call it going through A comma B with the radius of C. Let's draw a line perpendicular to there. So that right there would be pi by 2 plus theta, meaning that this angle right here would be theta. And we're on the same circle, so we have similar triangles because we have two shared angles. We have congruent triangles because we have one shared side, which means that the dimensions are the same, but the coordinates are a little bit different. There's a type of reflection and then inversion, I suppose. So reflected would get me negative A comma B, and then inverted would be negative B comma A. Maybe it's not exactly that combination, but I think you can see where the coordinates are. So if I look at the cosine of pi by 2 plus theta, which is going to be the ratio of x to r for pi by 2 minus or plus theta, that's going to be negative b to c, which is the opposite of b to c, which is going to be the opposite of the ratio of y to r for theta, which is the opposite of the sine of theta. If I wanted to check this work, I suppose. Now, the danger with checking work is, what are you going to do if you've proven yourself wrong? You have to take your loss and move on and try another question. But it might be nice to check and make sure that we're right. If instead we said the cosine of pi by 2 plus theta is equal to the cosine of pi by 2 times the cosine of theta minus the sine of pi by 2 times the sine of theta, so I'm using the cosine sum formula here, then I would get, well, the cosine of pi by 2 is 0, times the cosine of theta minus the sine of pi by 2 is 1, times the sine of theta, and 0 times the cosine of theta is 0, so I get negative, or the opposite of the sine of theta, which this time around actually seemed faster. So I want students to be flexible. I want them to be able to demonstrate their understanding through a number of different pathways. You shouldn't be memorizing which approach to use. You need to be ready for me to tell you to use one approach, but maybe you won't be sure which approach I'm going to tell you to use. Okay. These diagrams always bring up a conversation. One last thing that I want to mention. It may have come up when we were proving identities back in 5.2. Sometimes in grade 11, after we prove our primary identities, give me a sec here, sorry. Students stick to the strategy of writing identities in terms of XYR ratios. And that would have worked in grade 11 for every single identity. It's not going to work in grade 12 when we have double angles. You don't want to build your double angle formula by using XYR definitions. Okay, so while in grade 11 it would have been possible to do something like, like this, y over x plus x over y equals y squared plus x squared over xy equals r squared over xy equals r over x times r over y equals cosecant of theta times the secant of theta. It's not encouraged because it will only work when you have single angles. Okay, so I would strongly suggest that you stick to using your primary identities and not breaking down everything in terms of x's, y's, and r's. Let's go sine of theta over cosine of theta plus cosine of theta over the sine of theta equals the sine of theta squared plus the cosine of theta squared all over sine of theta, cos of theta equals 1 over sine of theta, cos of theta, which is the reciprocal of the sine of theta, cosecant of theta times the reciprocal of the cosine of theta. Okay, not recommended to always use XYR approaches. Okay, it's not always going to work. So don't try that out. Try our practiced approaches.